All right, let's take a look at some review for work and power calculations. The first thing I need to remind you of is that work is equal to force times displacement. Remember that both of these things up here, these are vector quantities, so they actually have directions associated with them. The way that we approached this in our class was we said that we were just going to put a constraint on this, that F, the force, must be in the same direction as the displacement if you're going to actually multiply the two things together. That means that sometimes we need to do some components to figure out a component of force or displacement. More generally speaking, recall that I said that there is two ways to multiply vectors together. There's a scalar product and a cross product, which is the vector product, and we are just dealing mostly with this strategy though, and so you're going to hear me talking about that. Let's just make a problem here to begin. Let us say that I am a person that is going to carry a bowling ball up a flight of stairs here. I'm going to say that I took a tape measure out and I measured the stairs are 10 meters, and we're going to give kind of an effective angle here of 30 degrees. My bowling ball here is going to have a mass of 5 kilograms. And let's also give me a mass here. Let's say that I am 65 kilograms. The first thing that I want to do is I want to say, do I do work in carrying the bowling ball up the stairs? And specifically, I want to just look at how much work do I do carrying just the bowling ball. And so I know that I just said that I'm 65 kilograms, but we're going to go ahead and take that into account in a moment. If you remember the free body diagram for the bowling ball, it would look something like this. There's an FG going down that is 5 kilograms times negative 9.8. And so what we're going to have here is we're going to have this downward vector that's negative 49 newtons. And then I'm putting an applied force on the ball that's equal to positive 49 newtons. Even though I'm going up the stairs and I am making some kind of horizontal progress here, there are no forces pushing in on the horizontal here. So we just don't have anything there because we are going to say two things. First, we're going to say we are not accelerating. We are only moving at constant velocity. And the other thing that we're going to say is that we don't have any air resistance that we're having to fight against. That simplifies the problem for us quite a bit, but what we notice is that this is the interesting force. If I say I want to know how much work am I doing as I lift the bowling ball up the stairs, there's my force, and it's vertical. The displacement that you travel is not vertical. I cannot just immediately multiply 10 meters by 49 newtons to find my answer here. What I need to do is I need to find the vertical component of the displacement, because that's the part that's going to allow for me to have the displacement in the same direction as my 49 newtons. And so over here I need d and the y. Well, to find that, I'm making kind of a triangle out of this with a 90-degree angle over here, and I'm going to say that the sine of 30 degrees is equal to the opposite side, that's my dy, the thing I want to know, times 10 meters. So I picked a nice number here where I can say that my dy is equal to 5 meters exactly. I also know that my F, the force that I'm applying to this thing, which is also in the y direction or the vertical direction, is 49 meters. So now I can go up here and I can say the work done on this bowling ball by me is 49 newtons multiplied by 5 meters. That means the work done was 245 joules. Remember, a Newton meter here is the same thing as a joule, and the joule is our preferred unit in the metric system for energy. Now let's incorporate my mass into this as well. Not only do I have to lift the bowling ball up, I also have to lift my own mass up. And so let's go ahead and combine the masses now. I'm going to say I have this amount of force that was associated with the bowling ball, but I also have some force associated with lifting my own mass up the stairs. So in part B, let's say here that we have 65 kilograms from me plus the 5 kilograms from the ball. So now I have 70 kilograms that I have to get up the stairs and that I have to actually do some work to do that. So this isn't going to change my problem too much, because now my new force associated with this is 686 newtons. You'll notice though that my total displacement was still from here to here, and that's the 5 meters that we solved before. So now the overall work for moving me and the ball is going to be 686 newtons times my 5 meters. I'm going to do 3,430 joules of work to get me and the ball up the stairs. We're going to get rid of some of that writing, but I want to hold on to that last number. So we had that our work was equal to 3,430 joules. I'm going to give us, call it a part C now, a problem where I say, in doing this work, I can exert a certain amount of power and stay comfortable. Let's say for me, I can exert 150 watts of power. And so I want to know, how long is it going to take for me to get up the stairs? So what I'm going to do is I'm simply just going to solve for T with my known information. So my power was 150 watts. That's going to be equal to the work done is 3,430 joules divided by T. That means that I'm going to end up with T equal to 3,430 joules divided by 150 watts. But remember, a watt is a joule per second. It's just a different unit. And so now I have second that's in a denominator that's in a denominator. That means that it flips up, just like 1 over x is actually the same thing as x. The importance of that is that I know from this that my time is going to be in seconds. And when I solve this out, I get 22.9 seconds. And so it's going to take me that long to go up the stairs if I'm exerting energy at that rate. So that's a power. So I'm using up energy at a particular rate. Conceptually, if I'm holding a bowling ball and I'm walking horizontally, I'm not actually doing any work whatsoever on that particular bowling ball, as far as physics is concerned at least, because the force that I'm applying is an applied force that's up. Remember, we're not accelerating and we're not allowing for any air resistance that we have to fight against, because the weight of the ball was down. And if your displacement is out this direction, then these two vectors are perpendicular to one another. They don't have any components that are in the same direction. That means when I do my operation up here, I'm going to end up getting a value of 0, because again, there is no component of either of these forces that can align with the other force. Also, if I drop the ball, I just completely let go of the ball, I cannot do any work on it. So something's doing work on it. It turns out that Earth is doing work on the ball to bring it downward. But I am not doing any work on it because I let go of the ball. I don't have any force that's touching the thing. If I lower the ball, so I just gently lower the ball, I still have a situation where I have F net equals 0. I still have to have this applied force on the ball, even though I'm lowering it at a constant velocity. And that means that I'm going to end up doing negative work, and that's okay. Let's just do one last little problem. This time I'm going to have my bowling ball sitting over here, and I've got it tied to a rope like I had in class. And I'm going to say that I have to pull in such a way so that this is 43 degrees and there's 20 newtons of tension. So I'm sitting here in this, I'm pulling the bowling ball over my shoulder here, and I'm just going to walk this way. And I'm going to make up a number. I'm going to say I walk 8 meters, and this force that's right here is coming about because I have to actually fight against friction. I'm not doing air resistance in this, but we are going to say that there are some frictional forces at the bottom here that ultimately are causing me to have some tension on that rope. So how do I figure out how much work I do dragging the bowling ball horizontally across the floor? My force is in this direction. My displacement is horizontal, so I cannot just multiply the numbers together. What I'm going to do is I'm going to figure out the components of the force. I don't really need to know the vertical component, so I'm not going to focus on it. What I do need is I need the Fx. I need the horizontal component, because that would align down here with my horizontal displacement. So I have 20 newtons sitting right here. Oops, I gave us this 43-degree angle there, so I'm going to apologize, but I'm going to go ahead and give us the complement angle of 47 right there. So now I just need to set up my equation here. So my Fx is actually going to be the opposite side over the hypotenuse. So this is going to be sine in this case. Sine of 47 degrees is equal to Fx over 20 newtons. So my Fx is equal to 14.6 newtons. I want to make sure I didn't cause any confusion over there with my drawing. Had I made my triangle like this, which would probably had made a little bit more sense because this was the angle I had, I would have been interested in this component, which is Fx. If that is what my triangle looked like, then it is true that I would have used the cosine function, so cosine of 43 degrees. So just remember to keep your trig straight. Is the adjacent side, Fx, over 20 newtons. But you know that those are going to actually produce the same thing for me. So the end thing here that's important is that I have 14.6 newtons of force that's actually in the direction of motion, and so now I can calculate my work. So now I have the Fx times the displacement, which was also in the x direction, and my work is going to be 14.6 newtons multiplied by 8 meters, and I get that I did 117 joules of work. All right, there you go. If it makes sense to you, let your computer know.